Friends, I am Yadamurthy. You are watching the video Chemistry Class 11 Part 1. Unit 2, that is chapter is Structure of Atom. In that chapter, the video 8th video today we are going to show, that is. In the previous class we studied about shapes of orbitals. In this class, now we can study about energies of orbitals. In the previous class, shapes of orbitals we have studied, that is 1s, 2s orbital, 3p orbital, 2p orbitals. What are their structures and the shapes? Those things we learned. In this section, energies of orbitals. This is one of the very important video. Let us start the energies of orbitals. Energy of an electron in a hydrogen atom is determined only by the principal quantum number. Energy of hydrogen atom can be determined only by the principal quantum number. Thus, the energy of the orbitals in hydrogen atom increases as follows. So you can see this as one. So 1s is 1s less than 2s, which is equal to 2p less than 3s, which is equal to 3p equals to 3d less than 4s, which is equal to 4p equals to 4p is equal to 4d and 4f. So this can be depicted in this is the picture, this is one. You can see this one picture, how the energy levels are determined: 1s, 2s, then 2p, 3s, 3p, 3d. Okay, the second figure, 1s, 2s, 2p, 3s, 3p, 4s, 3d, how the energy levels are increasing from 1s to 4f or 4p or 3d. The shapes of the 2s and 2p orbitals are different. The same in the last class you learned, no, shapes of 2s and 2p orbitals. There it is different, is that 2s and 2p orbitals are different. Electron has the same energy which is in the 2s orbital as when it is present in 2p orbitals. So same energy, electrons has the same energy when it is present in 2s and 2p orbitals. The orbitals having same energy are called degenerate. Where the orbitals having same energy, that is called degenerate orbital. The 1s orbital is a hydrogen atom, as said earlier, okay, correspond to the most stable condition and is called ground state. The 1s orbital is a hydrogen atom and which is corresponds to the most stable condition, that is ground state, and an electron residing in their orbital is most strongly held by the nucleus. Electron in the 2s 2p or higher orbitals in a hydrogen atom is in excited state. 2s or 2p or more than that higher orbitals are in the hydrogen orbital atom is in excited state. So the energy of an electron in a multi-electron atom, unlike that of the hydrogen atom, depends not only on its principal quantum number or shell, so but also it depends on azimuthal quantum number, that is azimuthal quantum number saying subshell. So principal quantum number says about shell and azimuthal quantum number says subshell. That is for given principal quantum number S, P, D, F and etc. all have different energies. Within a given principal quantum number, the energy of orbitals increases in the order S, P, C. You can see this is one. Energies of the orbitals increases in the order S is less than P, P is less than D and D is less than F. So for higher energy levels, these differences are sufficiently pronounced and staggering of the orbitals energy may result. Say for example 4s is less than 3d and 6s is less than 5d, and so 4f less than 6p. The main reason for having different energies of the subshell is the mutual repulsion among the electrons in multi-electrons. What is the reason? The different energies of the subshells in the is the mutual repulsion. Wherever the different energy of the subshells is the mutual repulsion among the electrons in the multi-electron atoms. The only electrical interaction present in the hydrogen atom is the attraction between the negatively charged electron and the positively charged nucleus. In multi-electron atoms, besides the presence of the attraction between the electron and the nucleus, there are repulsion terms between between every electron and other electrons present in the atom. Thus, the stability of an electron in a multi-electron atom is because the total attractive interactions are more than the repulsive interactions. Generally, the repulsive interaction of the electrons is the outer shell with the electron in the inner shell are more important. On the other hand, the attractive interactions of an electron increases with increase of the positive charge. So you can say that is Ze on the nucleus. Due to the presence of electrons in the inner shell, the electron in the outer shell will not experience the full positive charge of the nucleus. The effect will be lowered due to the partial screening of positive charge on the nucleus by the inner shell electrons. So this is known as the shielding of the outer shell electrons from the nucleus by the inner shell electrons. And the net positive charge experienced by the outer electrons is known as effective nuclear charge, that is ZEEFEFFE. Z effective. Despite the shielding of the outer electrons from the nucleus by the inner shell electrons, the attractive force experienced by the outer shell electrons increases with increase of the nuclear charge. In other words, the energy of interaction between the nucleus and electrons, say that is orbital energy, decreases. So negative, it will give negative with the increase of the atomic number Z. Both the attractive and repulsive interaction depends upon the shell and shape of the orbital in which the electron is present. For example, electrons present in spherical shaped s orbital shield the outer electrons from the nucleus more effectively as compared to the electrons present in p orbital. Similarly, electrons present in p orbitals shield the outer electrons from the nucleus more than the electrons present in d orbital, even though all these orbitals are present in the same shell. Further, within a shell, due to spherical shape of the s orbital, the s orbital electron spends more time close to the nucleus in comparison to p orbital electron, so which spends more time in the vicinity nucleus in comparison to d orbital electron. In other words, for a given shell, say principal quantum number, the Z effective experienced by the electron decreases with increase of the azimuthal quantum number L. So that is the s orbital electron will be more tightly bound to the nucleus than p orbital electron, which in turn will be better tightly bound the d orbital electron. The energy of electrons in s orbital will be lower, so that is negative, more negative than that of the p orbital electron, which will have less energy than that of d orbital electron, and so on. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to the splitting of energy levels with the same shell or same principal quantum number. So that is the energy of electron in an orbital as mentioned earlier. Depends upon the values of n and l. Mathematically, the dependence of the energies of the orbitals in n and l are quite complicated, but one simple rule is that the lower the value of n plus l for an orbital, lower its energy is its energy. So there is one simple rule is when the lower the value of n plus l for an orbital, so its energy is also lower. If two orbitals have the same values of n plus 1 L, the orbital with the lower values of n will be have the lower energy. If two orbitals having same value of n plus 12, the orbital with the lower value of n will have the lower energy. So you can see the below table arrangement of orbitals with the increasing energy on the basis of the n plus L rule. So you can understand that is one. These two simple rules. So it may be noted that different subshells of a particular shell have different energies in case of multi-electrons atoms. However, in hydrogen atom, there are same energy. So we can see the table here. 1s orbital having value of n is 1 and value of L is 0, then total value of n plus 1 L becomes 1 only. 1 plus 0 is 1. Same for 2s orbital having value of n value is 2 and L value is 1 0. So the total value of n plus L is 2 only. In 2p orbital, so total value of n is 2 and value of L is 1. So it becomes value of n plus L is 3. So and in 3s orbital, value of L is n is 0 and value of L is 3. So 3 plus 0 is equal to 3. So 3s nothing but n is equal to 3. So 2p n is equal to 2. When n is equal to 2 has lower energy than 3s, that is n3. N is equal to 3. In 3p, value of n is 3 and value of L is 1. So it will becomes value of n plus L is equal to 4. So here 3p has lower energy than 4s. So because 4s having n value is 1, L value is 0, then totally it will becomes n is equal to 4 or n plus L is equal to 4. And in the same way 3d orbital. So value of n is 3 and value of L is 2. Then by the total of n plus L is becomes 5. So here 3d n is equal to 3. So it has lower energy than the 4s or 4p. N is equal to 4. So 4p is equal to value of n is here 4 and value of L is equal to 1. Then so total value of n plus L is equal to 5. N plus L is equal to 5. Okay. Yes. So lastly, it may be noted that mentioned here the energies of the orbitals in the same subshell decrease with increase in the atomic number, that is Z effective. For example, energy of 2s orbital of hydrogen atom is greater than that of the 2s orbital of lithium, and that of lithium is greater than that of the sodium, and so on. So that is Z effective, Es is equal to Es having H hydrogen and is less more than E2s having Li lithium, and which is more than E2s in 2s orbital is gives sodium is more than E2s is more than potassium, and so on so on etc. I hope students this video understood about the energies of the orbitals. Thanks for watching the video. Thank you.